Swayam Prabha. Digital India. Educated India.
Today, we are going to discuss one of the thermal advanced micromachining process known as electron beam micromachining process. First, I will like to acknowledge the help in the preparation of this lecture by Professor Ajay Sethpara from IIT KANPUR and the chapter 12 on electron beam micromachining written by Ajay Sethpara and V.K. Jain in the book on Introduction to Micromachining edited by V.K. Jain, Narasa Publishing House, New Delhi. I also will like to acknowledge the help from the electron beam micromachining manufacturer site as given over here, and all these sites have been used to take some of the schematic diagrams or photographs related to electron beam micromachining which have been acknowledged, and then there are certain references from which we have taken some of the text or the photographs or the figures. They are mentioned over here. One of them is by Pierce, that was published, Pierce et al., Pierce and rectilinear, Pierce on rectilinear electron flow in beams, Journal of Applied Physics, and then Stigen-Bald, KH, published paper on Optic 5, 1949, 469. Now, the outlines of this particular lecture are as follows: introduction to the electron beam micromachining, components of electron beam micromachining setup or mechanism of material removal in case of electron beam micromachining, then various process parameters which affect the performance and the quality of the machine component, and there are certain issues related to micromachining in case of electron beam micromachining, and then some applications of this particular process. Introduction. Electron beam drilling was developed by Karl Heinz Steigerwald in Germany in the early 50s to drill holes in the jewel bearings for mechanical watches. In the year 1952, he built the first electron beam processing machine. In 1958, he butt welded 5 millimeter thick zircaloy together with the help of deep welding effect. In 63, he founded the company Steigerwald Strahltechnik in Germany. The electron beam, it is effective and highly concentrated source of energy. High velocity stream of electrons focused on the workpiece surface. We will see the mechanism of material removal, that how these electrons are able to remove the material from the workpiece. Material removal mechanism is basically the melting and vaporization of the workpiece material as common mechanism of material removal in case of thermal advanced micromachining processes. It uses kinetic energy of electrons while hitting the workpiece. That energy is converted into the heat, and which leads to the melting and to some extent vaporization of the workpiece material, so that the one gets the desired features and dimensions of the cavity. Electrically conducting and electrically non-conducting, both types of the workpieces can be machined, and it is not restricted to metals, non-metals also can be machined with the help of this particular process. Power density of thermal processes. There are various thermal processes as I just mentioned to you, and you will find that electric discharge EDM process has got more or less very high power density, that is watts per millimeter square, as you can see on this particular scale. This is the power density scale, and here is the spot diameter that you are going to get during the process, and you can see the spot diameter is not very large in case of electric discharge machining process, or this is also used for micro machining process. So, you can call it as electric discharge or electro discharge micro machining process. Then laser beam machining process also has reasonably good power density, as you can see over here, but in many cases lower than electric discharge micro machining process or electro discharge machining process. And then spot diameter is also not bad, it is around 10 raised to power 2 microns, that is around 100 microns, and lower size is quite low, reasonably good, as you can see over here. And this tells, with the help of this particular spot diameter, you can decide what kind of micro features you can create, because you cannot create the micro features smaller than the diameter of the spot or the diameter of the beam. However, all these beam diameters can be, in case of EBMM, this beam diameter can be further reduced through proper techniques. Then you have the electron beam machining process, and which has got very large range of the spot diameter, as you can see over here. This starts from here and goes up to this particular point over here. You can choose the diameter of the electron beam depending upon your requirement, and accordingly you have to set the process parameters. Then you have the welding arc, which has got reasonably high spot diameter, as you can see over here, which is shown over there, and then gas flame is there, which is still higher spot diameter. So, what does it indicate? That according to the requirement of the work, you have to choose the process parameter, so that you get the desired diameter of the beam, because this beam is going to decide what size of the features you will get. Then let us see the components of the electron beam machining or electron beam micro machining process setup. Now, you can see over here various components shown over here, as high voltage cable is there, and this is the cathode grid, here is the anode, and then you have the optical viewing system. Through this optical viewing system, you can see the location and some characteristics of the beam, electron beam, and here is the wall. Then this is the electron stream. Then you have the magnetic lens. We will see the function of these magnetic lens. With the help of magnetic lens, you can move the electron beam in x and y direction to some extent, not to a large extent, and then you have the deflection coil. So, this can deflect the beam in x and y direction, and this magnetic lens is used for concentrating the beam, and then you have the workpiece over here, and this is the beam hitting the workpiece, and now you can create very high vacuum in this machining chamber or this working chamber, so that you get a proper size of the machine features, and you can have high vacuum pump to create the vacuum in this particular chamber, and this is the viewing point what is happening in this particular machining chamber, that you can view with the help of proper devices from this particular viewing port. So, electron gun that consists of cathode, grid, anode, electromagnetic lens and deflection coils. So, this you can call as the electron gun, which consists all these devices as mentioned over here, and they have their functions that we will discuss. It generates free electrons, this should be FREE, free electrons at the cathode, and these electrons are coming out from the cathode grid and moving towards the anode, and then this is the valve, and here electron stream is coming out, and with the help of the magnetic lens you can make some changes over here in this stream, and then this is the deflection coil. So, it accelerates electrons to sufficiently high velocity. Now, this is very important. What is going to be the final velocity of the electrons will decide what is going to be the kinetic energy of each electron. Please note it carefully that electrons are normally considered to be massless, but still they have some mass, and with that extremely small mass, if you consider the velocity of the light, and if you calculate the half mv square of the electrons, you will find that large number of electrons can create very high temperature on the workpiece surface, such that it can melt and vaporize. So, this is the velocity of the electrons, which is going to decide finally what is going to be the kinetic energy of the electrons before hitting the workpiece surface. Focus the electrons over a small spot on the workpiece, as you can see over here. Cathode, it is a hot tungsten or tantalum filament that is shown here in the cathode grid. It is heated to around 2500 degree centigrade, which is quite high temperature. That is why thermo-ionic emission of the electrons takes place at such a high temperature in the cathode grid, and acceleration of continuous stream of electrons takes place because of the large potential difference. Anode is there, so they get accelerated and attracted towards the anode and pass through the valve. It is in the form of cartridge. Now, cathode grid, high negative bias is applied, it reduces the divergence of electron, that is very important. To operate electrons beam gun in pulsed mode, electron beam you can have continuous electron beam or you can have pulsed electron beam. So, depending upon your requirement of the machining features and the workpiece and the accuracy that you are interested in, you will decide whether it should be a continuous electron beam or it should be a pulsed electron beam. Many researchers are recommending pulsed electron beam for better accuracy and better quality of the machine features. Anode attracts electrons beam which gradually gets accelerated. This is the anode over here, and this is going to attract the electrons beam and it gets accelerated towards the workpiece. Electrons achieve the velocity as high as the velocity of light, very close to the, I should not say to the velocity of light, but very close to the velocity of light. Some people say it is half of the velocity of light. Valve, that is magnetic lens, is there, controls the beam shape and improves the quality of the beam. Electromagnetic lenses are there, magnetic lenses are there to focus the beam to a desired spot. As I mentioned earlier, used to focus the beam to the desired spot over here, and you can slightly move with the help of this deflection coil. It reduces the area of the beam, that you can see over here itself. From this diameter it is reducing, it is becoming taper and going down over there. Deflection coils to control the electrons beam movement to the in the required manner. So, this is used to control the movement of the electron beam. Basic elements of electron beam machining: to produce a high energy electron beam of a small cross sectional area. Three basic requirements for the construction of the electron beam machine are there. Just as you can see, a vacuum system, as we have seen, very high vacuum is created in the machining chamber. That question is, why do you need very high vacuum in the machining chamber? We will see its answer after a few slides. A vacuum system, this is combination of rotary and diffusion pump. It is providing sufficiently low pressure to allow the movement of the emitted electrons along the free path. This is very important, that if movement of electrons is not in the free path and it collides with other atoms or molecules of the air, then it is going to affect the performance of the process. An electron gun to produce high powered electron beam, and a focusing system to control the beam diameter in order to provide the necessary power densities for machining purposes. Because as I mentioned in the beginning, you can machine metallic components as well as non-metallic components, electrically conducting or electrically non-conducting. All kind of workpiece materials can be machined by this. However, you have to choose the right kind of values of the parameters, so that you can correctly machine the desired workpiece. The question is, why do you need vacuum in the machining chamber? I told you in the earlier slide that to create very high vacuum, you have the pump. The pumps are used to create high vacuum there. So, the question is, really speaking, why do you need it? In vacuum, 10 raised to minus 4 and 10 raised to minus 6 torr vacuum is created in the machining chamber. A clear stream of electrons bombarding the surface of the material. Electrons do not lose their energy. If vacuum is not there, then these electrons collide with the air molecules and they lose their energy. As I will just show you, it is easy and predictable cut if vacuum is there. If vacuum is not there, then you cannot predict the performance of the machining accurately. No oxidation problem is there if vacuum is there, otherwise the material which is being cut will get oxidized, and there will be so many other problems once the material gets oxidized, and you will not get the desired features, dimensions and accuracy. Without vacuum, a collision between an electron and an air molecule causes the electron to be disturbed or bare. Difficult to calculate the time and or beam intensity required to cut a part or drill a hole. Now, you please see here that this is the vacuum. In the vacuum, you can see the electron beam is moving more or less of the same dimension from top to the bottom, and it is the workpiece hitting the workpiece. So, when this electron beam is hitting the workpiece, you will get the diameter for which you have designed it, because definitely it is going to be a function of the diameter of the beam. But if vacuum is not there just like this, and if it is in the environment or atmospheric pressure is there, as you can see here, then what happens that this electrons of this electron beam, they collide with the molecules of the air, and you can see some of them are moving this way, some others this way or this way. Whole of this area is filled with the electrons, and you will not get the desired shape and size of the feature created on the workpiece. That is why it is always recommended that for high quality machining you should have very high vacuum. Although when you have high kinetic energy of this particular electrons, then probably situation may not be so bad, but you will not get the desired features on the machine workpiece. Now, this is a photographic view, as you can see here, hitting the, this is the workpiece, this is the beam which is hitting it and showing you different features. electron gun, the voltage on the anode of the electron gun provides the accelerating voltage to the electron beam, as we have seen in the earlier case. Cathode grade is there, then anode is there. So, the voltage on the anode of the gun, it provides the accelerating voltage to the electron beam. Pierce and Steiger-Wald systems, as I will show you there, they have been proposed, two different kind of the systems, as we can see here. This is the Pierce who has proposed this particular system. You can see indirectly heated over there. This is the electron beam, and this is the intersection over here, and then exiting from this particular section. Now, this is proposed by Steiger-Wald type. Now, here the characteristics of this electron beam are very different in this particular case compared to this one, and you can see the shape and size of the beam is very much different from Pierce type. And there is a third type which is known as triode type, and here again the beam shape and size are very different from the other two which we have just seen over there. And you can see that A is the anode, this is the anode, C is the cathode, this is the C is there, this is C is here, anode is here, C is here cathode, anode is here in this particular case. And then you have the G as the grid, this is the grid in all the three cases, and electron beam is here, this is the electron beam over here, and this is the electron beam, and X cross over spot is there. So, you can see that three different systems are there, or three different ways of the electron beam cross section are there, and definitely they are going to affect a feature being created in all the three cases. They have their own merits and demerits also. So, you have to carefully choose the machine which has a particular type of this system. Focusing system, electrostatic lenses are there which require very high voltage. They are used only for very low power machines. Electron beam assisted chemical etching purposes you can use this particular one, and then you have the electromagnetic lenses. They are used in all electron beam machining machines. Each magnetic lens consists of a coil of wire surrounded by an iron or steel shroud. It is sufficiently thick to about saturation. As you can see over here, this is a cross section of typical electromagnetic lens shroud. You can see this is the coil, and these are the cross sections of this. Now, this is the paper from where this reference has been taken. Now, let us see the electromagnetic lens design. Now, this is the electromagnetic lens. This design we have received with the courtesy of Dr. A.V. Bapat from Bhava Atomic Research Center, Mumbai. The E-beam emerging out of the electrostatic lens is a diverging beam due to diverging lens effect of the anode aperture. As we have seen in the earlier case, it was diverging, then later on it was intersecting later on. Coulomb repulsion between electrons is there, and thermal velocity distribution of electrons at cathode. So, electromagnetic lens is a device to provide a focusing action to this diverging beam. So, electromagnetic lens we had seen in the earlier case. A finite solenoid producing axis symmetric magnetic field serves the purpose, and identical to spherical convex lens action on the light rays is there. Now, the electromagnetic lens field distribution, as you will see here clearly, this is shown over there. Now, this is for the macro electron beam. As you can see, this is the length, and this is the kind of normal distribution in case of macro, but in case of micro it is highly concentrated, as you can see over here. So, this is quite different as long as field distribution is concerned in case of macro and micro. That is why in case of micron you have the feature size is smaller than a micron, than a millimeter. while in macro sizes you are having larger feature sizes, and this again was received from Dr. Bapat of Barg, Mumbai. Now, this is the typical electromagnetic lens parameters, and you can see here different parameter values are given and received from Dr. Bapat, as different elements are shown over here of the lens, and this is a specialized area of designing and developing the electromagnetic lens. Now, control console and electron beam generator. The control console consists of integrated CNC PLC monitor and control panel. Now, you can clearly see here, this is the control panel, different features are shown over here. This is the electron beam machining column, and in this control panel you can see the computer is there, display screen is there, control panel is there, right, and you can see electron beam machining column is here on the back side, which is shown over here, and different features are shown over here. So, with the help of these control devices you can control different parameters and the shape and size of the feature being machined over there. Now, workpiece chamber, the size of the workpiece chamber is determined by the size of the workpiece and by the machining or drilling application. We have seen in earlier slides, first one was the electron beam gun, and second one, bottom one was the workpiece chamber, where you had the workpiece, electron beam was coming, and then you had the devices to move in x and y direction to the workpiece, and lens for focusing the electron beam on the workpiece in a particular location. So, various workpiece manipulating units are available to sweep different workpiece types and drilling duties. So, it is really not exactly the drilling duties, you can say machining duties, because you can perform different kind of operation with the help of this particular beam, depending upon what movement in x and y direction you give to the workpiece with reference to the electron beam. So, configuration of the manipulator system is there. You can move in x and y direction, you can rotate it up and down, you can move, and you can rotate it also. So, this is how you can manage or manipulate the movement of the workpiece in x, y direction or rotational direction, and then beam is coming over there. So, the beam will interact with the workpiece and different features can be created. With this kind of the arrangement, you can create 3-dimensional features of micron sizes, and this will be very interesting, because you can move in x, y direction, in z direction, or in r theta direction, and so these movements are good enough for creating 3-dimensional devices. So, this has been taken from this particular reference that you can find out on the internet. Now, what is the mechanism of material removal in case of electron beam micromachining? Now, again the source is given over here. Mechanism, it is extreme heat creates a vapor capillary surrounding a cylinder of molten material. Molten material is there, and as I mentioned in earlier few slides back, that you are melting the workpiece material and part of it is getting vaporized. So, depending upon the system you have chosen and the parameters, you can have both melting as well as vaporization. As the depth of cut increases, the beam gets in the way of the molten metal, preventing it from escaping out of the hole. This is the one of the problem, that the performance or the efficiency of the process is not very high, because what is happening, that beam is coming over here, and in this way vapors of the molten material which is over here are moving up, but this beam prevents it from going out, and then this Again, if it is a pulsed electron beam, then during the off time it tries to solidify, then again go up. So, final efficiency goes down substantially. Backing material can be organic or synthetic. To produce a large volume, to expand explosively up the capillary up to 100 bar pressure, to expel the molten material and to maintain uniform size of the hole. So, you need the backing material, because what happens that when backing material gets heated up, it creates the vapor, and these vapors help this molten material to go out. And if this molten material is going out, then definitely the performance efficiency of the process will go up. And so, this backing material is used basically to expel the molten material and to maintain uniform size of the hole. Otherwise, what will happen if you do not do like this, or if you do not throw out the molten material, then with time this gets resolidified and you end up with what is known as recast layer, just like the recast layer you obtain in other thermal processes, say electric discharge micromachining or laser beam micromachining, and then it becomes really difficult to remove this recast layer before you are going to use the workpiece in real life. So, you can see here clearly that electron beam is coming, it is melting the workpiece material in the beginning, and you have the baking material over here at the bottom. You can clearly see this is the baking material, and this is the workpiece, and here melting is taking place, heating and melting is taking place. So, you have the molten material over here, and this is the baking material, and electron beam is there. So, what happens is that this baking material creates the vapors, and these vapors help this molten material from here to go out. So, you can see molten metal and gas, they are going out, but if electron beam is there in this direction, then this will prevent this particular phenomena, and the rate of removal of molten material from the crater or from the cavity goes down. So, if it is a pulsed electron beam micromachining, then definitely in the off time this phenomena will get expedited and you will get the better efficiency. Process parameters, electron beam micromachining process parameters, as you see here, there are various process parameters. Pulse duration, as you know that pulse duration, on time, off time and pulse time. So, depending upon your requirement, you can choose the on time of the pulse and off time of pulse. During on time, the electron beam will be hitting the workpiece surface and removing the material by melting and vaporization. During the off time, there will be no electron beam, and in this period vaporized material can go out of the cavity being machined. Then there is a beam current. Beam current is going to decide what is the total melting of the workpiece material, or what is the number of the electrons in the electron beam they are going to hit the workpiece. So, beam current is very important parameter for any electron beam micromachining process. Then you have the working distance. The working distance is also very important, because there is always a focus point for electron beam, and as you move away, as you move means as the workpiece surface moves away from the focus point, then the efficiency of the workpiece surface and the quality of the feature being created gets reduced. Then roundness of the beam, because it is not necessary that beam is always circular in nature. If it is not round, then you will get different kind of the features. If it is, because energy distribution is also different in case of round beam and different shape of the beam. So, you have to decide whether it is round or some other shape of the beam, and accordingly you will get the energy distribution on the workpiece surface, which will affect where from how much material is being melted out. the consistency of the beam diameter. If it is circular, then how consistent the beam diameter is, because as you are moving down and down of the workpiece, then the diameter of the beam will keep changing. As I mentioned, that if it is like this, then this is the depth direction. So, the beam diameter will keep changing, it will not remain the same, whatsoever small it may be, but it will change to some extent. Then symmetry and current of focusing length. Then vacuum system, we have seen that if you are not creating the vacuum, you are going to get, really speaking, inaccurate machine features or machine cavity. So, if you are working or machining under the high vacuum, then the accuracy and the quality of the machine feature will be quite high. And then movement of the workpiece, to create different kind of the features on the workpiece, you have to do x and y direction movement to the workpiece. Suppose here is the workpiece and here is the beam, and you want to create something like this. So, you have to move this workpiece such that beam is always there and you can create this kind of the feature over there. That means, you have to move the workpiece in this direction, because this beam will remain here only, beam is not going to move. You move the workpiece in this direction, that is the left direction, then this feature will be created. Once it is here, then you have to move the workpiece in y direction, so that this particular feature is created, and then from here you have to move the workpiece in this direction, so that this feature is created. So, you have to give relative motion to the workpiece with reference to the beam diameter to create any kind of the feature. So, for this purpose, you know it already, hopefully, that all these machines, they are normally CNC controlled, or they are controlled with the help of the software in x direction, y direction, or even to some extent in the z direction. There are certain parameters of the workpiece which will affect the performance of the whole process, just like a melting temperature. Depending upon the melting temperature, it will decide what should be the beam current, as is here, because that beam current is going to decide what kind of power you will get, or what kind of energy of the electrons will be there while hitting the workpiece surface. So, melting temperature, vaporization temperature of the workpiece is again important, because part of the material gets vaporized also, and that will be decided if by the vaporization temperature. If vaporization temperature is very high, then lesser amount of the material will get vaporized. If it is low, then definitely larger amount of the material will get vaporized. Then there is thermal conductivity. Again, thermal conductivity is an important parameter. This will decide how much heat is conducted away within the workpiece, because that is going to raise the temperature of the workpiece. Then another feature, another rather property of the workpiece material is the thermal diffusivity. So, what I am trying to tell is that all these workpiece material parameters, or properties rather, more correctly is the properties, they are going to affect the efficiency of the process, performance of the process, and quality of the features being machined. Then you have typical operating parameters. Now, these operating parameters are going to decide the performance of the process and to some extent characteristics of the features being machined. Just like accelerating voltage, it is normally, if it is low voltage, then less than 30 kilovolt, medium voltage 30 to 60 kilovolt, and high voltage 150 kilovolt. So, depending upon the workpiece material and the feature you are creating, you will decide whether it should be low voltage, medium voltage, or high voltage. Then beam modulations, continuous beam or pulsed beam, I have already mentioned to you that you get better machine component in case of pulsed beam rather than in the continuous beam. In continuous beam, you may get some kind of the defects created in the machine component, and especially in case of micromachining, it is always recommended in my opinion to go for pulsed beam rather than the continuous electron beam machining. Then vacuum, we have already seen the importance of the vacuum, that the whole efficiency of the electron beam machining is depending on the vacuum, what kind of vacuum you are having in the machining chamber. So, if it is high vacuum, then it will be less around 10 raised to power minus 5 or less than that m bar. If it is medium vacuum, that it is 10 raised to power minus 5 to 10 raised to power minus 3 m bar. Low vacuum greater than 10 raised to power minus 3 m bar, and atmospheric. If it is atmospheric, we have already seen what is going to happen to the electron beam. It will collide with the molecules of the air, and you will not get right kind of the feature created on the workpiece. Then beam power is there. Ultra low beam power is just few watts, low power is less than 6 kilowatts, medium is 6 to 12 kilowatts, and high power is greater than or equal to 12 kilowatts. And then another important parameter, operating important parameter is current, beam current 0.1 milliampere to 100 milliampere. So, depending upon your requirements of the feature you are going to create, you have to select accelerating voltage, beam modulation, vacuum in the machining chamber, beam power and beam current. So, it is important to select right kind or optimum, I should say, I can use the word optimum machining parameter to get the correct features generated over there. Then there are certain technical data of generator and chamber. I am not going to go into details. I will just tell you some names like accelerating voltage, which may be around 120 kilovolt. Beam current at workpiece we have seen 1 to 28 milliampere to 100 ampere. Maximum power. Now, please note it, in case of micro machining, these values may go down. These are more correct for larger size machining, maybe near to micro or macro machining purposes. And then you have maximum pulse power at workpiece, working distance something like 35 to 100 millimeter, 35 to 150 millimeter, 35 to 150 millimeter. You know, these are the different types of the generators. 3 types of generators are there: G33PM, G96PM, G120 PMF, and you can see depending upon the type of the generator you are using, the parameters that you are selecting for the generator are also changing. And then you can see the pulse length in terms of microsecond, it may be 50 to 30,000 microseconds. This varies, as we have seen earlier, that whatever is your feature requirement, accordingly you will decide what should be the pulse frequency and what should be the on time, what should be the off time. Then you are concerned with maximum frequency of spot following, it may be around 3000 or less than 3000, that will be decided what is the on time and what is the off time, or what is the total or pulse time. They will decide what is going to be the frequency. Then you have the chamber, machining chamber. Machining chamber volume, they can again vary on different types, K6, 12, K16, K19, K24. These are the different types of the chamber which have been standardized by the manufacturers. So, machining volume is in terms of meter cube, 0.63, 1.28, 1.63, and finally it is 2.54 cube meter of K24. So, you can clearly see that smaller volume machining chamber you can use for smaller workpieces, and larger volume machining chamber just like K24 good for bigger workpieces. Then diameter you can see 320 millimeter to 637 millimeter, and some of them like K16 and K19 have 1000 millimeter as the diameter, and then length is 400 to 950, it is varying and it is different for different types of the machining chamber. So, machining chamber dimensions you will decide based on the size of the workpiece. Please note it, it is size of the workpiece, not the size of the feature, because whole workpiece has to be placed inside the machining chamber, and then only you are going to create micro, nano or macro type of the features on the component being machined. Now, there are the issues relating to micro machining. Now, let us discuss some issues related to electron beam micromachining. Now, characteristics of electron beam machining or electron beam micromachining: cavity formation or penetration depth. It is a thermal and physical properties of material, because thermal and physical properties of the workpiece material are going to decide how much material is being removed by the given energy from the electrons, and they will decide the depth up to which the cavity is being formed. Characteristics of the electron beam, as we have seen, basically two types of the beams, that is, one can have uniform energy distribution across the cross section of the beam, another can have parabolic distribution of the energy across the beam, and they will decide exact penetration depth. Now, surface interaction of the electron beam with the workpiece material, the kinetic energy of the electrons is converted into thermal energy of extremely high density. Now, and this extremely high density energy, thermal energy, will result into the melting and vaporization of the workpiece material. To what extent depends upon the properties of the workpiece material and the energy being input. Now, material removal should take place before any substantial percentage of the heat is absorbed and it is transferred into bulk material. This is very important point, that quick material removal should take place. That simply means that molten material should be removed as early as possible from the cavity, so that the heat is effectively utilized in melting and vaporization, rather than allowing it to get transferred to the rest of the bulk material of the workpiece. This is very important, because it is going to govern the efficiency or the performance of the process. Then there is the heat affected zone, because when very large amount of heat is inputted and very high temperature of the workpiece material is there. So, what happens? Partial conversion of the workpiece material, metallurgical conversion takes place, and it damages the properties of the workpiece material in the neighborhood of the cavity being machined, just like this. Suppose this is the being machined, this is the cavity being machined, then certain extent this material will get affected, and the properties, mechanical and physical properties of this layer, these layers will get affected of the workpiece material, and this is known as heat affected zone. That means the zone which has been affected or changed or modified due to the heat being transferred from the molten material or very high temperature over here. This heat gets transferred and it affects this particular zone of the workpiece material, and that is what it is known as HAZ, means heat affected zone. Then efficiency of the beam, that is the rate of transfer of energy into the material. Whatever energy is being transferred to the workpiece material, that will decide how much amount is melted and how much amount of the material is vaporized and goes out, and that is what is the efficiency of the electron beam machining and electron beam micromachining. Rate of removal of molten vaporized material from the cavity, whatever this material is being removed, it should be quick. Whatever this material is being melted or vaporized, and molten material should be quickly removed, as well as vaporized material also should be quickly removed from the cavity. Otherwise, the efficiency of the electron beam micromachining is going to reduce. Now, another parameter is the cutting speed. So, it is recommended to scan the beam rapidly across the surface to be machined. Now, you can see clearly here, thermal diffusion zone is there. This is the track width where really the feature is being created and this is the scale 20 micron. and this has been taken from this particular journal paper, Microelectronics and Reliability, Pergamon Press. This is the paper from the journal. To minimize the thermal diffusion problem, to obtain narrow width of the cutting track. Narrower this width is, better the feature characteristics will be there, and you have to minimize the thermal diffusion, otherwise these kind of problem that adjacent layers of the workpiece material will get affected or damaged, and you should have controlled dimensions of the machined object. Now, conduction losses and temperature rise. Conduction, because molten material or the heat energy is in contact with the workpiece surface. So, definitely conduction of the heat is going to take place into the workpiece. So, principal cause of loss of efficiency in the heating process, because large amount of heat gets conducted into the workpiece material. So, the total amount of molten material reduces and total amount of vaporized material also reduces. It is advantageous to work with as small a beam as possible. That means, the diameter of the beam should be as small as possible in order to minimize conduction losses. Otherwise, conduction losses are large. Then the temperature of the workpiece material directly proportional to the beam power, electron beam power, and inversely proportional to the beam diameter. Definitely, larger the diameter, then more area of the workpiece will be covered. So, rise in the temperature will be lower. If the beam diameter is smaller, then the heat is concentrated into the small zone and the temperature rise will be higher. Then an increased spot size, an increased beam power is necessary for the same heat intensity. If you want to have the same heat intensity as in case of lower diameter, then you have to increase the beam power to get the same energy or same heat intensity as in case of a smaller spot size or a smaller diameter beam. Coarse machining with a rapid rate of material removal is possible. That means, you are not going to get good surface characteristics in case of coarse machining, but material removal rate or material removal rate may be larger, or the rate with which you are machining the component may be larger. Heat affected zone, it depends on the energy of the incident electrons, that is the current of the beam is going to decide the energy of the incident electrons. The diameter and distribution of the beam on the focused spot, as I mentioned to you, diameter and distribution of the beam on the focused spot, this is a focused spot, and you can have the beam over here, and this beam can have different shapes, as I mentioned to you, this shape or this shape, depending upon what kind of in what manner you are supplying the beam or you are having the beam over there. The nature of the target material, that is the workpiece material, what are the properties, as we have already seen, the parameters of the workpiece material which affect the heat affected zone as well as the efficiency of the process. Thermal diffusivity and thermal conductivity are going to control the heat affected zone, as I showed to you in the earlier case. This is the heat affected zone over here, and definitely this will be affected by the thermal diffusivity as well as thermal conductivity, because this is the molten material over here. So, the heat is conducted in all direction of the cavity. Then you have the rate of growth of heat affected zone, at what rate this heat affected zone is increasing or decreasing depends upon the magnitude as well magnitude of the heat or the molten material as well as the properties of the workpiece material. The final dimensions of heat affected zone are controlled by thermal diffusivity and thermal conductivity both. Melting and vaporization temperature, that tells that how much energy or heat is required for melting purposes and vaporization purposes. So, all this depends upon the properties of the workpiece material. It also gets affected by hardness after machining is affected, because it depends upon the cooling rate. Depending upon the cooling rate and the properties of the workpiece, the hardness of the cooled or solidified material will be governed. Highest at the entry into the hole and lowest at the exit of the hole. This is the entry of the hole. So, here you get highest one and lowest one at the exit. Suppose it is going out from this zone, then you will have the lowest at the exit of the hole. Beam, pulse beam operation, appropriately biasing the cathode grade, reduction in conduction loss. The material at the focused spot can be heated to high temperature before any appreciable conduction of heat can take place. High precision, reduction in spot fringe effects, mean rise in temperature of the workpiece is less. Low rate of absorption of energy by the material at the spot, low rate of propagation of temperature disturbances. Speed of the computer is a critical factor. How the computer system is going to control various operations in electron beam micromachining are very important.